Hello there. We're continuing with Chapter 3, talking about the Bernoulli equation, and we're going to continue and do sections 3.4 through 3.6 in this vodcast. The next vodcast then will be sections 3.7 and 3.8, and that will finish us off for Chapter 3. So, to begin, when we take a look at section 3.4 in your textbook, that's section we've already discussed a lot of the concepts and a lot of the specific ideas about Bernoulli equation. But basically, we rewrite Bernoulli equation, then we talk about the physical interpretation of the Bernoulli equation in section 3.4. So, for all intents and purposes, the most general, relatively useful form, in other words, for incompressible fluids, the most general statement of the Bernoulli equation is pressure over gamma, the specific weight of the fluid, plus V squared over 2G plus Z along a streamline is constant. Now, as we talked about in the last vodcast, you can see that the dimensions of the third term must be length, and specifically a height, because we're talking about the vertical direction. And that more or less corresponds to the concept of potential energy expressed in feet or meters. Similarly, if we take V squared over 2G, we can see that V, velocity, is length per time, and since it's squared, and then 2 is just a dimensionless constant, but G is in length per time squared. And if we divide that out, we see that we're left with dimensions of length here. And of course, we always had dimensions of length here. So then if we take pressure, which is in units of, dimensions of force per length squared, and divide it by gamma, which is weight or force per length to the third, we can similarly see forces cancel out, length to the third cancels against length to the squared and leaves us with a length in the denominator, which in the denominator of the denominator flips to the numerator, so we also have terms of length. So we are actually measuring energy in terms of a height. And the physical interpretation of this is, as we'll see later when we talk about some different types of measuring devices, is these terms will actually express themselves in terms of height. Or the height of a fluid can be exchanged for a velocity or a pressure, or any of those terms can be interchanged. Now, it's constant along the streamline. It's important to notice that that is in the absence of non-conservative forces such as friction. And in pipe flow, that's pretty unrealistic. So we can sort of gin up this equation in hydraulics, when we're not talking about it theoretically, to incorporate a loss due to friction or a loss due to the roughness of the pipe. But for now, we're assuming that the friction is negligible. All right, so one of the things that we can talk about then is each of these terms as a height. Z then is called elevation head, and head is just really referring to a height of fluid above some datum, some zero. The term V squared over 2G, because it's also in dimensions of length or elevation, is referred to as velocity head. And pressure divided by gamma is referred to as pressure head. Right? So when you write the Bernoulli equation in those forms, or if you're asked for the velocity head or the elevation head, that is specifically what we're talking about. So there are different types of devices that kind of separate these out. And we have to think about a couple of concepts before we can determine what those are. Just like we broke up pressure into absolute pressure, gauge pressure, and atmospheric pressure when we were in thermodynamics, we can now break up those ideas into, they're not the same exactly, but we can break up pressure into static pressure, stagnation pressure, dynamic pressure, and total pressure. All right. And we can express those in units of pressure. We could also, of course, express them as head, but we would need to use the weight of the fluid to then convert it back to a force per length squared dimension. All right, let's start. It's kind of easier to think about a static pressure. Static pressure is truly the pressure associated with the actual elevation of that fluid, so it's gamma times z. It's often referred to as hydrostatic pressure. Hydrostatic pressure is more commonly, or is more correct if we're talking about water, but it's often used for other fluids as well, and it's commonly understood to be gamma z. Stagnation pressure is the pressure that occurs at a point where the fluid is stagnant or not moving. So in other words, it is the pressure at the velocity equal to 0. Now, why would the velocity of a fluid equal 0? Well, there are some times, like if you have an obstruction, if you have a flow line and you have something that has to go around an object, there will be a place where the velocity vectors will split, and you'll have a point where you'll have no fluid flow at that point, or the velocity is equal to 0, and that's referred to as the stagnation point. So the pressure at the stagnation point, or the pressure where the velocity is equal to 0, is called the stagnation pressure. The other way you can think about that is, if you have a stagnation point, or if you have a pressure and you know what the stagnation pressure will be, that will be the pressure that will cause the fluid to have a 0 velocity. Okay, dynamic pressure is just the pressure associated with the velocity, rho v squared over 2, and then the total pressure is the sum. All right. So we have some different ideas, we have some different ways of thinking about those concepts. So we can think about them in terms of feet, or dimensions of length, or we can think about them in terms of dimensions of pressure. Really express the same ideas, just a different way of dividing it up. Now, in your textbook, they talk about measurements of static and stagnation pressure. And there's a good diagram on page 115 that shows how tubes in a fluid, a moving fluid, tubes put in a moving fluid can isolate out these ideas. And then on page 116, they have a very simple diagram of something called a pitot tube. And a pitot tube actually takes a moving fluid, and if you have a velocity, it's very simple. These are on airplanes, they're all over the place. I've seen them on dams even. But the velocity of the fluid as it moves has to be perpendicular to the opening. And you'll have something, the fluid could rise to some point. You could have an opening here, and you could have something up here. So these will measure different, you can actually take a look at what's going on in terms of dynamic pressure, total pressure, static pressure, by looking at differences in heights between those two points, 3 and 4. 2, 3, and 4, I should say. Okay. And once again, that's on page 116 of your textbook. All right, so section 3.6, I'm not going to, I want you to read carefully through 3.6, because what section 3.6 talks about are different applications of the Bernoulli equation. So once again, we're always going back to one of the forms of the Bernoulli equation, but just making a, let's see, let me just write it out in this form. Okay. This would be generally true along a streamline for an incompressible fluid. Right? So, and this is in pressure terms, of course. We could also divide by gamma and put it in terms of head, but this is generally true. They talk about different apparati and fluid that moves through them. For example, the first one they talk about is a free jet. And a free jet is takes liquid from a large reservoir and projects a jet of it out of some diameter from a nozzle and some velocity. And that's actually, I'm going to work a homework problem that's basically a free jet problem. So what we have is some fluid flow in a pipe, we have an obstruction in the pipe, and we sort of squeeze the fluid out along the sides of the obstruction. There are other types of appliances or apparatus that they talk about. They talk about confined flows, which is where you have a restriction in flow. For example, if you have something that necks down like this, and your streamlines are going to have to kind of be forced into some sort of a confinement, what happens at that particular type of a flow regime? And basically, the basic relating assumption here, or the basic relating fact, is that the mass flow rate here and the mass flow rate here are going to have to be the same. Even if the density or specific gravity are not the same, we're still going to have the same mass flow rate. And as you recall, Q, which is volumetric flow rate, is not necessarily conserved. It's only conserved if the fluid is incompressible. Well, if it is incompressible, as we've already had to assume for this form of Bernoulli, we can say that volumetric flow rate is conserved or is the same on one side and the other, but it's only because of the idea that Q, which is volume per time, and then you remember rho is equal to mass per volume, right? So if you multiply this by rho, Q times rho, you get what we used to call m dot, okay, which is a mass flow rate. This has to be conserved. So if you say Q times rho at one side of the confined flow equals Q times rho at the other side, Q at one side will be equal to one side if and only if the density values are the same. So since we've already had to make that assumption, it's fair to say that that is true. All right, so there are some other apparatus. They also talk a little bit about a weir. And if any of you have looked at any irrigation structures, a weir is actually an apparatus that they use in irrigation applications. And what a weir basically does is it measures flow geometrically. So there's a little discussion about weirs in this chapter as well. And then there was one other that I wanted to mention. Oh, it's not another device, but it's called cavitation. But what I want to get at with this, whether we're talking about a free jet, whether we're talking about a confined flow, whether we're talking about a weir, the principle is still the same. We still use the Bernoulli equation. It's generally applicable. Now, we may need to add to that Q times rho is also a constant, or if rho is constant, then Q at one point is going to equal Q at another point, right? And then remember that that's just the area of whatever it's flowing through times the velocity. So A1 V1 is also going to be equal to A2 V2, if and only if rho is constant. All right, so everything in section 3.6 talks about that. They also talk about this idea of cavitation. Now, a cavitation is a physical phenomena that occurs if the pressure of a fluid in a pipe drops below the vapor pressure. And how can that happen? Well, let's look at the Bernoulli equation, right? Let me put it back up here. If we want to reduce this, what do we want to do? We either want to increase this or both. So if we put something, if we increase the elevation of a fluid flow, which we can do just like in an irrigation tube or setting tubes for an irrigation project, or we can do it by increasing the velocity. Now, one thing you can do is, one way you can cavitate is, if you think about it, when you have fluid moving through a pipe, when you squeeze it into a tighter spot, the velocity will increase. Another thing that can happen is for velocity to increase, and this is actually a lot of people know this expression, is if you have a propeller on a boat. It's a really ugly propeller. But if your propeller is spinning very, very fast, you can get a high velocity out here and you can cavitate at that point. You can also cavitate pumps by decreasing the pressure with an increase in velocity. But anyway, cavitation is the phenomena of cavitation. It occurs if the pressure is reduced to or below the vapor pressure. What happens is that the fluid will actually cold boil inside of that confined pipe or whatever orifice it's in, or in the case of a propeller, it will if it cavitates on the tips of the propeller, then you'll have damage, because there's a lot of energy released when the bubbles are formed and then they collapse back in on themselves. It's actually the collapsing back in that will damage equipment. So that gets us through the end of section 3.6. The next thing that I would like to do before I finish this podcast is to work a problem for you from the homework set. And the problem that I've chosen is 3.87. All right. So if you look in your textbooks, problem 3.87 is we have a situation where we have a conical plug that is used to regulate the airflow from a pipe. All right, so we basically have a pipe. This is just the symbol for the open face of a pipe. And we have some Q going in here, some flow rate. We're told that flow rate is 0.5 cubic meters per second. All right, and the pipe, we have some dimensions on the pipe, and if we look at the flow in the pipe as the air enters the pipe, or as we are some point in the pipe, we don't really know how long the pipe is, what happens down at the other end of the pipe is that we put in a conical plug so that in profile the cone looks like this, and this is 0.2 meters high, and this is 0.2 meters high. And we basically squeeze the air out of these little, I don't know how you would say it, a little rivulet on the sides of the cone. Now, the picture in your book and the picture that I've drawn make this look quite wide, but we're told in the problem that the real thickness of this free jet is just 0.02 meters. So we're really squeezing the air into this very tiny little cone around, or little area around the cone. Now, in order to decide what that looks like, I want to turn this picture sideways, because what does the base of a cone look like? Looks like a circle, doesn't it? And if you relate this picture to the circle, we have a 0.2 meter radius of the circle, and the air is being squeezed out all around it in this little circle, and this little circle has a thickness of 0.02 meters. So this is the situation that we have. We have Q going in here, we have Q coming out here, and we want to know what is the pressure within the pipe. All right, so the first thing we do is we set up Bernoulli's equation. It does not matter which form, if you want to set it up in terms of head or if you want to set it up in terms of pressure, but I'll go ahead and set it up in terms of pressure. So we know that we're looking for the pressure in the pipe. So P2 plus V squared over 2G plus Z2. All right, so let's think about a couple of things. Well, first of all, this is essentially horizontal, so Z1 is equal to Z2. And the pressure, too, as we're going around this, these are free jets exposed to the atmosphere. And so that means that the pressure at state 2 is equal to 0 as well. Now, so now we know P1, we can find a gamma for air. We have a Q, we don't have a V here, but we can determine that based on a different equation, and same with this V. Well, how do we relate velocity to flow rate? We know that velocity times area is equal to flow rate. So we know that the velocity at point 1 in the pipe times the area of the pipe is equal to Q, which we're given. So if we want to solve for V1, we can just say V1 is equal to Q over A1. We know that Q is 0.5 meters to the third per second, because we're given that in the problem. And the area of this pipe is pi r squared, or we're given a diameter. Let me just look at something here. We are told that the diameter is 0.23 meters. So we can use pi r squared, or we can say pi times d squared divided by 4. All right, so that will give me my velocity at in the pipe. So this 4 actually flips up to the top, doesn't it? So on the top, I have 0.5 times 4, and I divide that by pi. And I divide it again by 0.23 meters raised to the second power. And I get a value of 12.03. Let's check units. Meters squared on the bottom, meters third, so that cancels. Per second. Meters per second, good unit for velocity. All right, well, let's take a look at velocity at 2. We also know, similarly, that velocity at 2 is the same Q over A2, but our A2 is a little different. It's the ring around that cone, because that's where all the air is coming out. So it's really the area of this circle minus the area of this circle. So it is, the area of a circle is pi r squared. And so it's going to be pi times the outer radius minus the inner radius. Or I can say pi times r times h, 2 pi. That's not right. That's not right. Sorry. A circle is need to get this, I'm sorry, I'm just having a little bit of a momentary lapse of reason. If the radius around the cone, the radius of the cone is 0.2 meters. Okay, and the height of that, or the difference between here and here, is 0.02 meters. There we go. And then I multiply that by 2 pi. I will get the area of that circle, the thick circle. So the flow rate is still 0.5 meters cubed per second. The area is going to be 2 pi times 0.2 meters times 0.02 meters. And that value, meters cancels this, and I'm left with meters per second. So that's a good unit. I get 0.5 divided by 2 pi divided by 0.2 and divided again by 0.02, and I get a value of 19.9 meters per second. All right, now this number is significantly higher than this number, and that makes sense, doesn't it? Because we're squeezing it out around the side of the cone. All right, well, if I go back to this equation, I can say P1, which is what I'm looking for, over gamma, plus V1 squared over 2G equals V2 squared over 2G. Now, solving for P1, am I still on the page? There we go. That's going to equal V2 squared minus V1 squared over 2G. And I know that I have a relationship between gamma and rho, which is rho times G. So, in other words, I could multiply through by gamma, and I would get on the left-hand side of the equation P1, and on the right-hand side of the equation I would get V2 squared minus V1 squared. Now this gamma is going to be rho times G, and that's over 2G, so my G's cancel out, and I just get times rho divided by 2. So P1 is equal to rho over 2 times the quantity V2 squared minus V1 squared. And then we're going to have to check units, make sure I haven't, I'm pretty sure that's good, but let's just double check. All right, so P1 then, continuing with the calculation, is equal to 1/2 times the density of air, which I would look up in the inside front cover. Now, since we're talking about air, it's going to be a little squiffy, because in terms of gases, we know that we've got some compressibility, but we're basically assuming that the number's going to stay about the same. And so I get a value of 1.23 kilogram per meter cubed from the inside cover of your book. So you get 1/2 times 1.23 kilogram per meter cubed times the velocity at 0.2 squared, 19.9 squared, minus the velocity at the beginning, 12.03 squared, and that's in meters squared per second squared. Okay. So P1, then, let's just double check. Let's go 19.9 squared (396.01), 12.03 squared, which is 144.72. And if I subtract those two, I get 251.29. Okay, and then I'm going to multiply that value by 1.23 divided by 2, which is 0.615. And my answer for P1, before I check my units, is 154.5. All right, so now let's go through my units. Meters squared cancels here, right? So I have, I should do this a little bit differently. I know that a kilogram meter per second squared is a Newton from force equals mass times acceleration. So I'm going to just divide this up meter, meter, right? And then I'm going to leave this one, but I'm going to cancel this against this, and instead of being 3, it'll be to the second power. So I have a kilogram meter per second squared, which is a Newton, divided by a meter squared. So my pressure at point 1 is 154.5 Newton per meter squared, which the SI unit for that is a Pascal. All right, ladies and gentlemen, that's it for section 3.4 through 3.6. When we come back, we're going to discuss some more implications of the Bernoulli equation. And if any of you have worked in civil engineering, you may have seen a hydraulic grade line or an energy line. We're going to talk about drawing those, but they come directly from the idea of expressing Bernoulli equation terms as elevations. So we'll see you then.